Okay, good evening, everyone, and welcome to tonight's talk by Dr. Amanda Quirk, By the Stars' Light, Exploring Stellar Spectroscopy. We are delighted to have you all joining us tonight at the Stavros Narcos Foundation Library. My name is Jackie Trailis, and I am a member of the programs team here at SNFL. Before we start, I would like to thank the Stavros Narcos Foundation for making programs like tonight's possible. I would also like to remind you that if you don't already have a library card, it is easy to get one by visiting any information desk in this building, so you should do that or renew yours. Finally, I would like to encourage you to visit NYPL's website and take a look at upcoming 7 Stories Up programs like this one. We would love to have you join us in this space again. And now let me introduce tonight's speaker. Dr. Amanda Quirk did her undergrad at Columbia, inspired to study astronomy after seeing Saturn in a telescope at an observatory in Atlanta, Georgia. She completed her PhD at UC Santa Cruz, where she studied the evolutionary history of the Andromeda and Triangulum galaxies. During graduate school, she discovered her love of teaching and returned to Columbia after graduation as a Frontiers of Science Fellow. Now, she is a lecturer in the Astronomy Department at Columbia and runs the outreach program. Without further ado, please welcome Dr. Quirk.
Hello. Thank you all so much for being here. I'm really excited to share this with you all. A couple of things to add to my bio that are important for you all to know tonight. One, I am from the South, so you will hear y'alls from me throughout the talk. And the other is I'm a teacher, so I require class participation. All right, so with that, let's get started. Since we have a wide range of prior knowledge levels in this audience, we're going to start with some basic vocabulary. So this talk, if my clicker wants to work, all right, we're going to talk about stars and galaxies. Stars are giant balls of gas and plasma that have energy and heat and light coming off of them that are held together by gravity. This is the most commonly known star, the sun, giving life to our planet. And on the right, I have a picture of the Andromeda galaxy. It's one of my favorites. Galaxies are made up of stars and some other things I don't personally care about, like planets and black holes. So these objects are so cool that we want to study them, but we can't go to them and run experiments or take samples. And that's because space is really big. The universe is too big for us to fly to anything beyond our solar system. So the only way we can learn about stars or galaxies is through their light. And there's 2 ways we can study their light. We can take a picture, just like you can with your phone or with your camera, and we get these incredibly beautiful images. I'm showing the Pinwheel Galaxy on the left, the Eagle Nebula in the center, and the swirling clouds of gas on Jupiter on the right. So these images are incredibly beautiful, and they're important for us to learn about how things look, where things are in the universe. But we can do something else to study the light, and that is instead of looking at it all at once, we can spread out the light. So this is similar to putting light through a prism. Our eyes can see visible lights. That usually looks like white light coming from lights in our homes, in buildings. And when we put that white light through a prism, it spreads out all of the individual kinds of light that make up that light, and we see a rainbow. So when we spread out the light, it's called a spectrum. So now we have a spectrum of an object, and this practice is called spectroscopy. We don't only do this with visible light, but we do this with all the different kinds of light. So the electromagnetic spectrum, all of the different kinds of light we have in the universe, from radio waves to gamma rays, that's all different kinds of light. And visible light only occupies a really teeny tiny portion of what's out there. So even if you are sighted, you are blind to the vast majority of the universe. So in order for us to get the full picture, it is critical that we look at all different kinds of light. And when we do this spreading of the light, when we do spectroscopy, we learn two things about an object. And we're going to be talking about stars specifically. So the first thing that we can learn is the kind of elements that are in a star. So the periodic table of elements, what chemicals, even what molecules are in a star. And we can figure out how fast the star is moving. So I hope that feels or sounds very powerful to you all. Just by looking at a star's light, I can tell you what's in it, and I can tell you about its movement. So I'm going to explain the first portion of this talk is for me to try to convince you that A, we can do these things, and B, they're worthwhile doing. So I'm going to first start with how we can learn about these two things. And I'm going to talk about something called absorption lines. So we have our star, and we take its light and we send it through something like a prism, and we expect to see a rainbow. So the spreading out of light, our eyes can see the rainbow. There's other light in there as well, but for the purposes of this talk, I'll just be showing rainbows to represent spectroscopy. But in reality, stars have atmospheres. So the light that is made in the center of the star and that travels all the way out has to pass through its atmosphere. And the atmosphere actually blocks some of the light. So instead of seeing that complete rainbow, we see a rainbow with gaps in it. So black bands where there is less or no light. And these bands are called absorption lines because the atmosphere has absorbed some of the light. And that maybe sounds annoying, like wouldn't we rather have all of the light? But actually, it's an incredibly wonderful phenomenon that allows astronomers to uncover the secrets of stars. And so I'm going to explain why, but just so you all know, this is a picture for teaching and outreach purposes. And this is what a picture of spectra, so multiple spectrum, look like. So they've rotated them 90 degrees now. Each of these vertical stripes or vertical bands is the spectrum of one star. So this is about 50 stars all at once. And here, the horizontal white or bright bands, those are the absorption lines. So we have the glamorous teaching image and the kind of boring science image. So we don't get those beautiful images when we do spectroscopy. It's pretty boring. I'm allowed to say that because I do this kind of work, but we learn a lot from it. And so when, as I said, the light passes through the star's atmosphere, some of the light is blocked. This leads absorption lines. And it turns out that these absorption lines correspond to different elements. And that each element has a specific pattern. And we know this because we can burn an element in a lab, and we can look at the light that's coming from that burning element, and we can see that it always has the same pattern, and that its pattern is distinct from all of the other elements. So you can think about this as like a fingerprint. Each element has a fingerprint. I'm showing 4 examples here: sodium, nitrogen, hydrogen, and oxygen. And you should notice that each of them have different patterns of absorption lines. They're in different places, they're different widths. They don't line up. So when we see these patterns in the light of a star, we know those elements must be in that star. So it's like putting together pieces of a puzzle. Of course, it's fairly complicated because stars don't just have one element in them. And when they have multiple elements, these patterns add together. So this is a fictitious element A and fictitious element B. Here are their individual absorption line patterns. And if they're both present in a star, the star's spectrum would look like this. So just adding the patterns together. So it can be very complicated when stars have a lot of elements in them, and also molecules. So molecules have their own pattern as well, like water or carbon monoxide. And astronomers, we tend to not analyze these pictures of a spectrum. Instead, we convert the picture to a graph. So on the top, I'm showing a picture, and on the bottom, I'm showing a graph where we put the amount of light on the y-axis and the wavelength of light, so the kind of light, on the x-axis. And what you might notice is that the black band in the picture of a spectrum corresponds with a dip in the graph. So if we didn't have any absorption lines, it would be a smooth curve, but instead we have these wiggles. And it's not that necessarily all of the light at this wavelength is being blocked, but a lot of it is, a significant amount of it is. This is, again, a nice rainbow picture for teaching and outreach. In reality, we just get black squiggly lines. So these are spectra from stars in the Andromeda galaxy. So it might not look like a star to you, but you're looking at 3 different stars in our sister galaxy. Okay, I hope at this point I've convinced you you can learn about the elements in a star. And we're going to talk about now how you can figure out how fast a star is moving. And so we know those patterns exist in a star. We know where the pattern should be because we can do those lab experiments. But sometimes we see the patterns have shifted. They're not where we expect them to be. They're a little to the left or a little to the right in the spectrum. And if we see a shift, then we know a star is moving. This might sound foreign, but it's something that you all experience on Earth. So imagine you are standing out on the city street, this is you, a fire engine with the siren on approaches you and then passes you. So as the truck approaches you, how does the sound change? This is the class participation part. Okay, it gets louder. How else does it change? The pitch, what happens to the pitch? It's higher, okay? And then what about when it passes you and now goes away from you? How does the pitch sound? Lower. So is someone in the fire engine saying, that person, I'm going to trick with them, and they change the pitch as they approach you and then lower it as they go away? No, the fire truck doesn't care about you. Neither do stars. What's happening is that the sound waves that the engine is releasing, as if they're in front of the moving truck, they get squished together. If they get squished together, their pitch or their frequency goes up. And if they're trailing the truck, they're kind of like being left behind. So they get spread out, their pitch decreases. I'm going to show an animation of this. So we have 2 videos that are going to play in a moment. In each, the red circle at the center is our source. So this could be our fire engine that's giving off sound, or it could be a star that's giving off light. Light is a kind of wave. It's different from sound waves, but it is a wave nonetheless. These blue circles you'll see coming from the source, those are the wave. So it could be a sound wave, could be a light wave. On the left, the source is not moving, and on the right, the source is moving. So on this left, where the source is not moving, the waves are evenly spaced out as they leave the source. So if a star is not moving, or you're not moving and the truck is not moving, you would hear the same pitch of sound the whole time. But on the right, where the source is moving, the waves in front of it get squished together, and the waves behind it get spread out a little bit. This happens both to sound and to light. And so what this looks like for spectra is if we have hydrogen, let's say, the first element on our periodic table of elements, it has a fairly simple absorption line pattern. This is where we expect to see it. And then if we looked at a star that had hydrogen, we might see that the absorption lines don't match up perfectly. The pattern is the same. We have two kind of close together and then two that are more spaced apart. So we know it's hydrogen. But again, it's not exactly where we expected it to be. It's systematically shifted to the right. In this case, is redder light. So that tells me the light got squished a little bit, so the star is moving towards us, is moving towards Earth. Okay, let's try it out. So, what I'm going to do in just a moment is bring up what's called a Jupyter Python notebook. None of you need to know how to code. There's not going to be a quiz later. But astronomers do so much data processing. So almost all astronomers code in some language. Python is the most popular language for astronomers. We're going to be looking at stars from the Andromeda galaxy. We'll look at two stars that were taken on the Keck telescope. And so I'll talk about that telescope after we get through the nitty-gritty of spectroscopy. Okay, so we have our spectrum of a star in Andromeda. This time I've colored the line red. That doesn't have any significance, but the black squiggly lines are kind of boring, so why not a red squiggly line? Do you see absorption lines? Yes, okay, we see some pretty prominent ones. Whenever we want to learn about a star, we need to compare it to what we know. And we know things from experiments like burning elements in a lab and also using computer models or computer simulations. So we can make a fake star on our computer and we can pretend to observe it and see what it would look like. And then we compare that model or that template star to the real star. And that's what I'm going to add now to this graph. So now the red squiggly line is still the star, but the black squiggly line is our model, is our template. So our fake star that we're going to use to learn about this star. Is it a perfect fit? Does the model resemble the star perfectly? No, and we would be a little concerned if it did. There are a lot of stars out there. We cannot perfectly predict what one of hundreds of billions of stars is going to look like. Is it awful? Is it totally different than our star? No. This is where astronomers have to get comfortable with shrugging and saying, good enough. You know, we're not engineers. When engineers shrug and say good enough, the buildings in Midtown start to buckle. When astronomers say good enough, we learn stuff about the universe. So this is good enough. There are some areas here, it has the same shape. They both go up. Here, this area, I would say, is where there's the biggest difference. So we just won't look at that area. And instead, we're going to zoom in on another part. So right now, I'm just going to zoom in so that we can see those absorption lines better. And what I've zoomed in on is called the calcium triplet. 1, 2, 3 absorption lines, and it is a signature of calcium. So we've learned that there is calcium in this star. Do the model and the star absorption lines line up perfectly? No. So what does that mean about our star? It's moving. Congratulations, all stars are moving. That's not a big surprise. It actually is really annoying to do work in astronomy because everything is moving, so it's really hard to disentangle one movement from another. But yes, the absorption lines don't line up, which means this star is moving. And so you all now have to help me figure out how shifted the model is from the star. So what we're going to think about first is, do I want to move the black line to the left or to the right so that it lines up with my star? Okay, I'd agree, to the left. So we're going to do a negative shift. We want the wavelengths to be smaller. Now let's focus on this absorption line because it's the clearest one. I want this black peak to line up with this peak. This line corresponds to 8,550. This one corresponds to 8,500. So we're looking for a number that's smaller than 50 because this needs to shift only a little bit, not all the way from here to here. So I would love to hear some guesses. The most fun part about this is you just guess and see what happens. We're not committed to it. We're not going to publish this paper. We're just going to see what happens, and then we're going to try again if we don't like the outcome. So let me hear a number. Okay, I heard 40, so let's hear 40. And I'm going to the left, so I'm going to make it negative 40. The black line is going to move. All right, did the black line move? Did we do too much? All right, we overdid it. So we say, that's fine. Let's just change the number, erase that like it didn't happen. All right, let's hear 10, okay. Okay, it's still too much, but that was closer. Another suggestion, please. All right, I like this. Let's just keep halving. Okay, that looks pretty good. This is where, as astronomers, we have to decide, is that pretty good enough for us? We can get way too anal about this and try to get it exact, but for this purposes, we'll say that's good enough. So what we did is we moved the template 5 times 10 to the negative 10 meters. This is an incredibly small amount. This is thinner than a human hair. You need a very powerful, fancy lab microscope to see. So our eyes don't notice this. We need machinery to notice this difference. So this is a really teeny tiny difference, but let's calculate how big of a shift that was. So how fast is the star moving if we had to shift its spectrum by 5 times 10 to the negative 10 meters? So this is where pick your units. If you did science class in the US, like unfortunately I did, then we're going to go with miles per hour. And so that's almost 400,000 miles per hour. Is that fast or slow? It's very fast. It's faster than humans can go on Earth. It's about as fast as our fastest satellites or spacecraft out there. So stars are moving incredibly, incredibly fast. And because we had to move the template to the left, it turns out that star is moving towards us. Okay, let's do this one more time with a different star in Andromeda. So still same galaxy, same telescope. The color here doesn't mean anything. I just made it a different color to differentiate it. Does this star have absorption lines? Okay. Let's look at our model. So it's a different type of star. So we have a different type of model. How does the model fit? Yeah, pretty good. Good enough for me. Okay, so let's zoom in on another absorption line. So we have a step, and a step. So imagine, this one has a little bump in it, but imagine it goes like this, like a smile. So we want to move like the template a little bit also to the left. So left means we're going negative. Can I have a suggestion, please? All right, let's start at negative 5. Okay, so if we think this dip and this dip, I think we overshot it a little bit. I have another suggestion. Okay, let's try negative 3. This one's a harder case because the absorption lines aren't super clear, but I think that's pretty good. So let's see what that velocity corresponds to. And it corresponds to over 200,000 miles per hour. So this star is still moving very fast. It's also moving towards us. And this kind of analysis is what astronomers did to determine that it's not just the stars or a couple of stars in Andromeda, it's the whole galaxy. The entire galaxy is moving towards the Milky Way, towards us. Yes. Yeah, right now they're so far apart from each other that they will not collide now. The Milky Way and the Andromeda galaxy might collide in 5 billion years. They might not, but they are coming towards each other. All right. Well, congratulations, everyone. You are now astronomers because you did some data analysis. You get PhDs. I spent a lot of my PhD doing that. Now, in reality, that's not actually how we calculate the velocity of stars. We have computer programs move the template over the star's spectrum. It's much faster, it's much more accurate, but it is the same process. So hopefully I have convinced you that spectroscopy, even though we don't get beautiful images from it, it's still worth doing because we can tell what's in the star and how fast it is moving towards or away from us. So unless anyone objects, we're going to observe now. So we'll observe, or we'll mock observe, the Triangulum galaxy, which is my favorite galaxy. It's a spiral galaxy like the Milky Way. This is a real image of it. It's 100 times less massive than the Milky Way. So it's a relatively small galaxy, and it's 3 million light years away. This means it takes light 3 million years to leave the galaxy and get to us. So really, I spent 6 years studying what this galaxy looks like 3 million years ago, and I can't tell you what it looks like today. But anyway, this galaxy has 40 billion stars in it. And with spectroscopy, what we have to do is isolate each star. We can't have all of the stars shining at us at once because then their light overlaps. So when we do the analysis looking at their absorption lines, we would get some from one star and some from another star. So since we have to isolate all the stars, do you all think we could do this with all of the stars in Triangulum, with 40 billion stars? Let's do raise your hands for yes, raise your hand for no. A room full of pessimists. But you have good intuition. And to answer this, I'm first going to have us think about how much actually is a billion. I personally think that word has lost some of its meaning. I say it's a billion degrees out all the time. Our governments spend billions of dollars all the time. There are 8 billion people on the planet, so it's a fairly common number on Earth. But to help us think about how much this is, I'm going to ask, can you count to a billion? Okay, the pessimism is continuing. But again, good instincts. I feel confident that you all know the numbers between 1 and a billion. So it's just a matter of time. So let's think about how long it would take you to count to a billion. If we pretend that it would take, so there are 1 billion numbers, and if we pretend that it takes us about 5 seconds to say every number, this is an estimate. The small numbers I can say really fast, 1, 2, 3, 4, 5. The big numbers, 562,324, that takes me longer. There are more big numbers than there are small numbers. So this might even be a fast estimate. That would take me 5 billion seconds. That means nothing to me. Is that 2 days? Is that a year? So let's do some unit conversion. 5 billion seconds is 158 years. And remember, I didn't take into account sleeping breaks, breathing breaks, drinking breaks, eating breaks, say goodbye to your social life. So a billion is a huge, huge number. And for another sense of scale, the record, oops, I clicked too much. Let's go back. Okay, the record of the longest counting was done in 2007, and he counted to 1 million for 16 hours a day, which is far more than I work in a day, and it took him 89 days. So I hope that also gives you a sense of how much bigger a billion is than a million. 89 days, that's not even a year. versus 158 years. That is more than humans have ever, like a single human has ever lived for. So a billion plus a million is still just a billion. Okay, so you all were correct. We can't do this with the stars in Triangulum, with all of them. They're far too many. And if we actually take into account all of the realistic conditions of observing, like the fact that Triangulum has to be up in the sky, it has to be during the night, it has to be during good weather, I have to look at each star for 2 hours, it would take 220,000 years to do this with Triangulum. And I personally would like to retire sometime, so I can't do that. Maybe one day we'll have the technology to do that. So instead, we have to pick the stars we want to observe. Just pick a couple thousand of 40 billion. That's a hard thing to do. But the goal of my science was to discover what is happening in the galaxy, what might have happened to it in the past. So I want to pick stars that kind of represent the whole population. So do you all think I want to pick boring stars or interesting stars for that goal? Hearing interesting, I'm hearing both. All right, it's actually boring stars. I want to pick stars that I don't think are special or exceptional, that represent the whole. And I'm going to talk about now how we do that. So this is kind of my setup. I have the Triangulum galaxy, and then I point my camera at it. And my camera is a very skinny rectangular field of view. So this is like how your phone doesn't see everything your eyes can see. Sometimes you have to step back so you can fit everything into the picture. Our telescope has a very skinny field of view. And within this field of view, there are stars I want to observe, but there are far more stars I don't want to observe. That would be like if standing here, I wanted to take a picture of you all, but I only wanted the people wearing glasses. So how can I do that? How can I only take a picture of the people wearing glasses with just a single photo? Okay, ask all the people with glasses to move together. I could definitely do that right now. It might make people feel sad that they're not in my photo. But the thing with stars is they don't listen to me. They're, first of all, not going to get my message. Triangulum is too far away. And they certainly would say, yeah, no, thank you. I'm going to stay where I am. So great suggestion, just doesn't work for space. Any other ideas? Special kind of camera. Special kind of camera. We could do that, but most of the stars here are going to be the same enough that a camera is not going to differentiate between them. Over here, I heard use a filter, and that is very close to what we do. So if I wanted to take a picture of just the people wearing glasses, I could put a piece of foil over my phone camera and just poke holes that correspond to the people who are wearing glasses and line it up just so that my phone only sees the people wearing glasses. And that's what we do on the telescope. We have a piece of metal that we call a slit mask. It's a flimsy piece of metal, and we carve little slits into it. The slits line up with the stars that we want to see, and they block out all of the other stars because the starlight can't go through the metal. From afar, these slits look one-dimensional, but they're actually a little box, and our star is in the middle. These slits are also very useful because the light of the star is stretched out vertically. So that's how we get our spectrum. So there's a limit to how many stars or how many slits we can put on a mask because they can't overlap vertically. We don't want their light to be contaminated. Yes. Yeah, So, how do we know the star didn't move? We're planning for these observations. Your intuition is telling you that this has to be very precise. And we also just did a demonstration that showed that stars are moving hundreds of thousands of miles per hour. So, they are moving that fast. But the thing is, these galaxies are so far away, we don't get to see that movement. And that's something that's really hard to conceptualize. The stars are moving so fast, but if I look at them today and I look at them in a month, they're going to be in exactly the same place. Even if I look at them in a couple of years, they'll be in exactly the same place because these galaxies are so far away. Yeah, so the Earth is moving, and that means we can only do this when Triangulum is in the sky. And so that's only a couple of hours a night because the Earth is rotating, Triangulum will be in the sky, and then it will start to set as the Earth continues to rotate. Okay, so we design these slit masks with a piece of software called D-Simulator. This program is so old that there are 2 computers in the world that can still run it. At least the last time I did this, so everyone's very nervous. And this program, I give it a list of stars that are in the area. All of these green and little blue slits on the software, this is the shape of my mask, are potential stars. It tries to optimize to get as many stars on there as possible, but not let them overlap. Once I'm happy with this design, it creates a map like this, and then I send it to the observatory. They take a piece of metal and they drill the slits into the metal. And then we get, they're just like a millimeter in thickness. They can be different lengths. So this is a zoom in on one slit mask. If you ignore all the fingerprints on it, you can see there are slits. These slits have different lengths, but they're all about the same thickness, so just like a millimeter. And we have a box. This is called an alignment box. It's the most important thing. You'll have 6 of them on a mask. And that's to help make sure the mask is perfectly positioned. So do we need to rotate it a little bit? Do we need to move it up or down so that all the stars we want line up perfectly with this slit? The first time I did this, I was so terrified. I was so convinced we were going to start observing and none of the light would come through the slits because I had done something wrong. That didn't happen, but I was genuinely very nervous about it. So we have all of our observations plans. Then we need equipment. So how we do this is telescopes focus the light. All they do is collect the light. They don't analyze it. They don't change it. They just collect the light and they send it to an instrument. In this case, our instrument is a spectrograph, which is like a prism, and it has our slit mask on top of it so that we only see the stars that we chose to see. Then a camera captures the spectra. So captures the light just the same way the CCDs in your camera capture light in your phone. And then the camera sends the light to a computer for it to be processed by humans. The instruments and telescope that I use are the Keck telescope and the Deimos spectrograph. On the left is the Keck 1 and Keck 2 telescope. They are identical telescopes, but they have different instruments on them. In the middle is what Keck 2 looks like. And on the right is me with Deimos. I know I am small, but Deimos is quite big. So before I talk more, I want to acknowledge that these telescopes are on Mauna Kea, which has always been and continues to play an extremely significant cultural role to the Indigenous Hawaiian community, and we are very fortunate to be able to observe from this sacred space. The Keck telescope is one of the biggest telescopes on Earth. It is 10 meters or 30 feet across. To help us visualize that, do you all think it would fit in this room? You can hear yeses or nos. Yeah, I'm not great at estimating. I make my students do a lot of estimating. This year, this direction would be really tight. So if it this way, it would fit. But it would take up the majority of the room. So this is a really, really big telescope. It also weighs a lot because it's big. It weighs 30 tons. Sorry, 300 tons. Thank you. I undersold it. 300 tons. But this telescope needs to move incredibly precisely and quickly, and it can't shake while it's moving because, as someone mentioned before, the Earth is rotating, so things move in the sky. So to move it very smoothly, they actually have it floating on pressurized oil. So this massive telescope that is 300 tons is floating. The telescope is so big that you can't have the mirror be a single piece of glass. It would be too heavy, it would most likely get misshapen, and if you broke it, you would really be in trouble. So instead of a single sheet of glass, they have 36 hexagons that are pieced together and curved precisely so it's as if there is one singular mirror. These segments are fairly big. This is the back of one of them, a hand for scale. And you can also maybe notice there are all of these pistons on the back, and these things poke the mirror so that it's bent in a way to make a continuous, slightly curved mirror. These segments are much easier to take and clean and replace or fix if they're broken. Keck also takes a lot of data and uses a lot of power, so there are just closets full of hard drives and circuit boards. So it takes a lot of people to get this observatory working and to keep it functional. As I mentioned earlier, Keck is on Mauna Kea. Mauna Kea is the tallest mountain on Earth if you count from the bottom of the sea. It's 14,000 almost feet above sea level, which means you can get altitude sickness. You will get altitude sickness if you go up. There are several telescopes on Mauna Kea. They all have different policies. Keck has the most conservative policy. It says, astronomers, you are not sleeping. You are experiencing altitude sickness. It turns out you're really bad at driving down the mountain after all of that, so you don't get to observe from the mountain. Instead, we're in an old cowboy town called Waimea on the big island of Hawaii. And these are the dorms that you stay at. And you can look up and just see the domes on Mauna Kea. And we're observing remote. This is another picture. I really love this one right before sunset. It looks like the domes are floating in the sky. All right, so on a typical observing day, it starts at 4 p.m. So this is where you go to what's called headquarters, the observing room. You look at the telescope and you start to do some tests. You want to make sure you understand how the camera is working, how the instrument is working, so that doesn't bias your science at all. But you're not allowed to start doing that until the engineers are done with the instrument for the day. So we can take a look, we can spy on Keck and see. It's going to take a moment to come up and see what's happening tonight. So Hawaii is 5 or 6 hours behind us. So the instruments, I'm looking at Keck 1 and Keck 2. I'm going to zoom in. Okay, Keck 1 and Keck 2. All of these are red, which says that it's not ready. So the astronomers cannot start doing their tests. You have to just keep refreshing until these turn green. We can see that there are 2 instruments being put on Keck 1 tonight and 2 instruments being just 1 instrument being put on Keck 2. We can see the names of the astronomers, the names of the support astronomers. So they're the ones who know how the instrument works and make sure that the astronomers don't mess anything up. And then we also have the names of the telescope operators tonight. And the fact that there are 2 instruments on Keck 1 and 1 instrument on Keck 2 also tells me what the schedule is for tonight. So for both of these teams, they're going to start at 4 p.m. Then hopefully they're done with their tests around 5:30, so you can go get an early dinner. You can get lots of snacks and whatever is going to keep you caffeinated. For me, that's a fruity green tea. And then it depends on the shift that you have. So, of course, it depends on good weather. I'm not going to check the weather on Keck because this website only works at nights, but we frequently get weathered out, including blizzard outs, because Mauna Kea is so high that there is sometimes snow on it. So then you can be at the beach and look up and see the snow on Mauna Kea and stay at the beach because you know you're not observing. What you really hope for is that you get a full night of observing. So this is from sunset to sunrise. So truly, whenever it is dark, you get to use the telescope all night. My personal favorite, because I'm a bad astronomer, is to have the first half night shift. This is from sunset to about midnight. And I like it because it means I get to go to bed at a reasonable time. The absolute worst shift to get is midnight to sunrise. So you try to sleep until midnight or 11 p.m., and then you wake up and you're observing until about 6 a.m. when you would then go to sleep, making sure you're awake by 4 p.m. to take your calibrations. And how you get scheduled into one of these depends on how compelling your science is. When your science item is up, it might only be up at 3 a.m., so then it's kind of your fault that you're observing in the second half night. And so you don't get to control the telescope. You're on Zoom with the telescope operator. You ask them to move the telescope, but you do get to control the instrument. So this is the instrument control panel for Deimos. And there are a bunch of different things that I can select, including what slit mask I want to use. In a moment, I'm going to play a video, which is actually a recording of me and, at the time, my PhD advisor, Professor Raja Guhathakurta, observing on Keck. And so I'm going to spoil it for you, tell you what's going to happen, and then I'll play the video. You're going to hear Raja explaining the setup. You'll just see the computer screen, not us. You'll hear the computer say, exposure complete. That means it's done taking images, and it's going to start processing, sending the data from the camera to the computer. You'll hear me say I'm going to change the slit mask. You'll hear the telescope operator say he's going to move the telescope to our next target. Then you'll hear readout complete, which means the data went from the camera to the computer, and then you'll see our raw data.
Good. In the meantime, it is almost finished, the exposure. So you can see 1043, 1044. When it hits 1050, you'll hear a voice saying exposure complete.
Exposure complete.
Okay, and now
I'm going to change the mask if they want to see that.
Oh yeah. So what Amanda's going to do is change the mask to a different metal plate.
Yep, I'm slowing now.
Thank you. So this thing that went gray over here in this part, it's because Amanda's requested a change in the instrument configuration. A different metal plate is being moved in where the old one was, a different mask. And we're also changing the tilt of the grating to go from first order to zeroth order. The object name is also something that we will change. Instead of PTH1, it will be PTST2. And that's something that will reflect a
ECD readout complete.
You could see that it updated, I don't know if you could see, but it updated the image of the spectra.
Okay, so that is what it's like to be an astronomer. We sometimes have visitors, they're tired, it's 3 a.m., they saw how hard it was to set up, they're so excited to hear that the picture is coming out, and then they look at the black and white lines and go, oh. It's like, yeah, okay, it's not a beautiful image, but as you all know, these spectra tell us about the composition of the stars and how fast they're moving. So we take this raw data, we use computer simulations to computer programs to clean it up, we make our black squiggly lines, and then we learn about the stars. And if you want to join astronomers using Keck and other telescopes, Raja started an organization called Shadow the Scientist that let you Zoom with scientists, astronomers, and other scientists like oceanography as they're working. So you get to see that it is boring and tedious, but you get a really good glimpse of what it's like being a scientist. You can talk to them during downtime. The sessions pop up kind of sporadically. They're free. Everyone is welcome to join. And if you want to learn more about astronomy, Columbia hosts monthly talks and stargazing. They're free and open to everyone. Campus is closed to non-affiliates, so you do need to register ahead of time. The best way to make sure you're registering is to join our mailing list at outreach.astro.columbia. Our next talk is actually this Friday, but I'm going to be giving this same talk, so maybe don't come to that one. But our next one after that is August 28th, and if the weather is good, we will use the telescope in the dome at Columbia to look at galaxies and other things in space. All right, and with that, thank you very much, and I'm happy to take questions.
Thank you so much, Amanda. So yes, we do have some time for some additional questions, and I'm just going to bring a mic around so that the live stream audience can hear it too.
I was just kind of curious, with the slits in the filter, you know how zoetrope works? It spins around, and I'm wondering if any tests have been done by spinning kind of the data of the stars and seeing what results.
Yeah, so since we're not capturing any physical properties, we can't spin, I might be misunderstanding your question, but we can't spin the starlight because we don't have anything physical. And the stars, we need to spend about 2 hours focused on the star to get enough light to see it, so we can't have any movement during that time.
What are some of the biggest mysteries or questions in astronomy that you hope somebody solves?
Yeah, great question. I would say one of the biggest is the idea of dark matter. So it's named dark because it doesn't interact with light. We can't see it. We can't build a detector that can see it. And it's also called dark because astronomers are in the dark about it. We know it has to exist from studying the movement of stars. Stars are moving too fast. They should be flung out of the galaxy that they're in, but they're not. They're still a part of the galaxy. So that tells us there's missing mass that we don't see. And you might think with this attitude of good enough, maybe we're just bad at counting the mass, but we're missing 90% of the mass. And astronomers, we are more accurate. We're better than that. So there's something about the universe we don't really understand. We know it must be there, but we don't know what it is.
I think I saw one over here. No? Okay. Yeah. Oh, all right. I got this one here.
What is your criteria to determine what stars you will select to study?
Yes. And so part of that is we can only look at stars that are bright enough for our detector to pick up. So I said that we have to look at each star for about 2 hours, and that's because Triangulum is really far away. So there are some stars that if we pointed at them, after 2 hours, we still wouldn't have enough data to really look at absorption lines. So we look for stars that are bright, and we look for stars that are isolated because we don't want their light to be contaminated with other stars. So this means we have to look at stars where pictures have been taken of them. So like when we see a picture of Triangulum, we can zoom in and look at the stars, see which ones are isolated and bright, and we pick those. But we're still only picking a really, really tiny portion of all the stars in the galaxy.
Okay, and now I have this one. Did I miss this side? No? Good. Okay. Here, I'm coming.
First, thanks for a wonderful program. I really enjoyed it. I have several questions. First, about exoplanets. Have you ever, during your studies, come across a star where the light was pulsing brighter and dimmer due to the rotation of a planet around that star?
Yes. That's what you're describing is how exoplanets are detected, or one way, and that is you're looking at the brightness of a star, and if a planet passes in front of it, its brightness dims a little bit, and then it goes back up when the planet moves. I never saw that, and we can't see that in our data because we aren't looking at stars for long enough. 2 hours is not long enough for most planets to pass in front of the star. And we're not looking at the light in the right kind of way. So we couldn't detect that.
Okay, my other question that I wanted to ask you was about the actual composition of these stars. Obviously, you're having changes due to red and blue shifts. Are there any other changes that take place? Since you're observing for long periods of time to capture the light, have you noticed chemical changes, let's say, due to reactions or I'm trying to think like changes in the photosphere of the star, actual chemical changes that are occurring?
Yeah, for the most part, stars live for millions of years. So kind of like how I said earlier, if I look at Andromeda today and look at Andromeda or Triangulum years from now, it's going to look exactly the same. For the most part, that's true with stars as well. So we would have to get really lucky to be looking at a star at the right time to see it have like a small eruption, like a nova, or something like that. Our data might also not be high enough resolution to detect chemical changes.
Okay.
Since you mentioned novas, supernovas, etc., have you or anybody on your team ever speculated or considered the possibility of a black hole in this galaxy?
Yeah, so we know there is a black hole at the center of Triangulum and the center of Andromeda. Or we know for Andromeda, we think for Triangulum. It's hypothesized that all galaxies have some kind of supermassive black hole in their center. Just from galaxy evolution. But we don't study black holes. I don't study supernova, so we haven't investigated that personally.
I want to see. I think we have time for maybe one more.
Are there other things that you can know about the star by studying light, like age, or are there other ways to study those type of characteristics?
Age is actually the hardest thing to know about a star. We can learn things like what evolutionary phase it is in. Is it in the main part of its life? Is it towards the end of its life? We can know how hot its surface is. We can know what color it would appear to our human eyes. But age is really, really hard. And so there are other techniques that I don't do to try to study the age of stars and to figure that out. But it's really, really hard. So not with this technique.
Okay, we're going to do just one more.
I was just curious, you said the part that turns the light into like the spectra, is that, you said it's like a prism, but like maybe it's hard to explain, but what is it actually? Like, is it glass? Is it, I don't know, yeah, what material?
Yeah, it's called a diffraction grating, and it's kind of like a mini staircase. So light is going to hit it at different cutouts, and that will make the light bend differently. So in the same way that the glass in a prism makes the light bend differently, and that's why it spreads out, this kind of staircase makes the light bend differently and therefore spread out.
All right. Dr. Quirk, thank you so much.